especially when you're doing like an upper or lower sum. Because it's like an upper sum is not always the left sum or the right sum, it depends on the shape of the graph. So for some of those, you just have to do more work. Right. But then the trick is knowing what the work is. So none of it should be overly complicated for a Riemann sum. The big issue is just doing the right work. And if you have a picture, definitely use the picture to help you. On the homework, had you drawn a picture, it would probably been a lot easier to do most of them. Alright, so that's this one on this exam, or quiz. We wanted to approximate the area using a Riemann sum doing midpoint method with 3 rectangles. So what I would have done, given this graph and everything, you could say, okay, I need to divide this into 3 rectangles, so each one should be width 2, right? And then where are the midpoints? How do you find the midpoint? If I know this is my first interval, this is my midpoint value, right? So how do I get the height? From the formula it says literally plug this value into the function to get the y-coordinate, or just trace up here and say here's my y-coordinate, that must be the height of my rectangle. And then once you've drawn this, can you find the area of it? This height is 5, so width times height, 2 times 5. I know this rectangle has area 10. Then I go to the second interval, -1 to 1. Midpoint would be 0, plug that in. I'm sitting up here at y equals 9. So the area of this would be 18. And then I do the same thing over here. So I get 3 rectangles. I know the area of each one. Add them together, you get 38, right? Did I need to do xk, a bunch of awful notation? Looking at it this way, does it make a lot more sense to see it? Use something like that to help you. Right? You don't.
That straightforward. I mean, for the most part, is there like more basic ways to work around instead of using notations? Would you say so?
I mean, I think to me, if I have the graph and I can draw like this is almost, in my mind, this is infinitely easier than notation and using the formula. When do you have to use the formula with no exceptions?
If it says to?
Yeah, if it says fair. The only problems where you had to use the formula, in some sense, were use the definition to find the definite interval. So we're trying to find this definite integral. It's defined as the limit as n goes to infinity for Riemann sums. There you can't draw a picture and do n rectangles and set n to infinity. It's like when we say n equal 3, n equal 4, you could draw a picture for that, right? When you send n to infinity, you're kind of stuck. So for those, you have to plow through the whole formula and just do it by the definition. All right. How many of those do you think will be on the test tomorrow? That was a big concept is we can define definite integrals using Riemann sums and taking the limit. So in some sense, we have to put it on the test. But it also takes a while, so it's only going to be one problem. All right. So there will be one of those on the test. You can expect it. We have some of those in the notes, especially for what I did in class, and we share those on the videos and all. So just doing everything by definition. When you do it by definition, what do you have to do? You have to find the delta x value, so that's b minus a over n. So for n rectangles, you just put an n here, right? But in general, I know n, I can plug it in, I get number 2 for this example. And then you need to know the xk values. So that's always a plus k delta x. So we need that formula memorized. If you've done a bunch of these, they're kind of awful when you do like a plus k delta x. You get awful things to expand. Sometimes we'll set a or b equal to 0, and then suddenly it makes the work easier. All right, especially for that formula, a plus k delta x. If a was equal to 0, this is way less effort. So there are ways we can make these shorter than what you see in the homework. The homework is by far the worst it could ever be. Some of those were meant to basically involve everything, so don't expect the absolute worst case example of it. But you do have, if you understand the one in the homework or the notes, that was the more tedious example, that should make the test one that much easier. So if we know xk, what is the next thing we need to do? So we know delta x, we know xk. Where's our formula? It's always sum of f of xk star times delta x. Does this formula make sense now? It used not to make sense. What is it saying? Y coordinates times the width. That gives me all the rectangles. So height times width gives me the area of a rectangle. Add them all together. Put the sum in front. Looking back, this notation is a little more clean or clear, hopefully. What's the big thing? You need to know which numbers to plug in, right? So what is xk star? That's when it depends. Am I doing a left sum, right sum, midpoint rule, upper sum, lower sum, trapezoid? Well, trapezoid you can't plug in one. But then that just means when you pick xk star, it's going to be based on xk, right? Like for a left sum, it's xk minus 1. So I'd replace k with k minus 1. For a right sum, it's just xk, which is nice. I can just copy the formula. If you have to do this by hand and we don't specify, which one should you choose? It's a lot easier to let xk star just be xk and not even worry about the star part. So that's always a right hand sum. So usually when you do it by hand or by the definition when you take a limit, you do the right sum just because it's easier to write notationally. What about the midpoint? What do we have to do there? I'd have to do like x0 plus x1 divided by 2, find the average value to get the midpoints. It's like when you do this one, you could do that with just the xk formulas. And this one's a little easier, right? If I know these are my x coordinates, between -3 and -1, the midpoint would be -2. Between -1 and 1, the midpoint is 0. It's like when you have you should be able to match these two when you're going. And then the last thing is just plug it all in, right? So this is going to be what, 3 terms? The height or the width is always the same. I can factor that part out. So then it's just saying plug in f of the right value, f of -2, f of 0, f of 2. So these are just my y coordinates. Once I know all these, add it all up, multiply by 2, I get 38. And then what you really, ideally before the test, what you want to convince yourself is these are the same solution. Like one's plowing through notation, one's labeling a graph, but can you make sure they correspond to each other? Right? If the notation makes sense, it would then make the definition part easier. Let me do it that way. What would change here if I said find it by definition? This would be sum k equals 1 to n. And just add limit and then goes to infinity up front. So then what's going to change over here? All of this will involve some k's and n's in it. Eventually we use those summation formulas. When you use the summation formulas, it gets rid of all the k's, and then you can just take the limit as it goes to infinity. So if you get rid of the k's first, then you take care of the n's. Which is what we have on the back of this page. So like if you can go through how to set this up in general, and then do this type of computation, that means you can actually put the two together and do that full limit definition problem. These are the 2 skills that you need for that type of problem. Yeah?
I'm kind of confused for the plus n after you, for the number 10. Yeah, number 2, sorry. When you've got the formula for n, k equals 1 k squared, but there's still that plus 1. Why did it become an n? I kind of forgot.
I'll get to that in a second.
Oh.
Yeah. So how would we do this one? This one, if you're going to approach something like this, so you add up a bunch of things, and then you take the limit as n goes to infinity. Notice all these have k's in them, right? So our goal is really, can we get rid of the k's? Once you get rid of all the k's, then you can take a limit. And I will give you the same formulas on the test. Alright, so you will have this at the bottom of the page where it's relevant. It's not even like here's the formulas on the first page. It's when you do the limit definition, go to the bottom of the page, it has these formulas. Hopefully that's the only time you really need them on the test. If you use them everywhere, that could be a problem. Alright, so if I wanted to rewrite this, I could move this in cube outside. I can only move it to here, right? Since it doesn't have a K in it, it doesn't have to be to the right of the summation symbol. Anything with a K, I can't move past the sum. Anything with an N, I'm allowed to move out to here. I can't go all the way out because it's inside the limit. So if I move this one out and factor it, what's left? It would be the sum of K cubed plus 1, or sorry, K squared plus 1. So I can write that, I can break that into two sums, right? So then what do? I go to the bottom of the page, it says, oh, this came up in the homework. In the homework it started at 3, which meant you had to then correct it. Here it starts at 1, all the formulas start at 1. So look at the bottom of the page, sum from K equal 1 to N of K squared is exactly this value. What's nice there, I've gotten rid of all the K's, right? It told me what this adds up to. So I already did most of the work on that part. What about sum from K equal 1 to N of just the number 1? So we give you the formula, but then what does this one say? Take the number 1, add it to itself n times. So if you add all those up, you get the n.
Yeah, I totally forgot that.
It's easy to skip around. So then what? I need to take the limit, right? How do we take limits? Usually you just want a single fraction on top, single thing on the top, single thing on the bottom to figure out what's happening. So I can multiply everything by n cubed on the bottom, and then start cleaning these up. So I can expand that one. If I do all the expansions, I get this. There are different ways to take limits. You can do L'Hopital's rule, you can do a bunch of things. What I did was just broke it up, right? 2n cubed over 6n cubed. This simplifies to 1/3. The 3n squared over 6n cubed, that'd be 3 over 6 is 1/2. N squared on top, n cubed on the bottom. I get another copy of n on the bottom. Or I keep one of these. So n over 6n cubed would be 1 over 6n squared. One of the n's cancels off. Because I have just this single thing on the bottom, I can do this, right? And then same over here, 1 over n squared I can leave. So then what happens? Now I can send the limit as n goes to infinity. So I can plug in infinity, what would happen? 1 over infinity is 0. 1 over infinity, 0. 1 over infinity, 0. All these kind of smaller order terms go away. I'm only left with this 1/3. So the limit must be 1/3. Any questions on that one?
Why are the formulas for the summation given at the bottom? Why are they given to us in the expanded formula? Aren't we going to have to like multiply them out every single time to do that?
Probably. You mean, why is it not like k plus 1?
Yeah, like first thing.
Like in a lot of the homework problems, we gave you things like this. So then the first thing you do is either shift your index or multiply this out.
Yeah, I think I was thinking about like when you give us the.
Oh, why are they factored?
Yeah.
Historical.
Right. Huh?
Historical reasons.
Oh.
It's the cleanest way to write them. There's no great reason other than they factor nicely. Yeah, it's annoying because you expand them every time, and that's like 3-4 lines worth of work sometimes. Yeah, I don't have a great answer. I mean, they look nicer this way, but it's not a great answer. Yes?
Is there a reason that you opted to distribute the n on the outside in the first fraction rather than just using that n to cancel with one of the n's on the bottom? Is there a reason for that?
Why I distributed here into this stuff?
No. The like on the first fraction where there's the n by itself, like
Oh.
in the factored form.
Right here?
No. Like, okay, when you have the first after you distributed the 1 over n to the third.
Yes.
But like, why not use one of the n's from the bottom of that
Oh,
to
I
cancel
see.
with
yeah,
the?
There's no good reason. I could have said, make that a 2.
Yeah.
There's no good reason.
So basically, you did it just for the sake of doing extra work.
Yeah. Usually I don't. I try to write what's the easiest to follow, not what's the best one. But then that's always a judgment call. There are lots of ways to do some of these. As long as you show work and it's justified, that's good enough. Yeah, like a lot of these, I mean, in some sense you could look at this and say, what's the limit going to be? It's going to be the leading term, 2n cubed. Anything else is dominated by 2n cubed. So there are other shortcuts kind of built in based on how we get limits. I always multiply it all out and show every step just to make it that much convincing I'm not missing something. But any other questions? This one didn't really have 4-1 on it. 4-1 is, or no, I guess this was technically a 4-1 problem, but make sure you look back at summation notation and how I use it. Like we kind of introduced it, but then we always used it in the exact same way every time after 4-1 because it only showed up in Riemann sums. So make sure you just glance over 4-1 in those examples kind of quickly to remind yourself really all of what was in 4-1. We only used one part of it for the rest of chapter 4. All right. The difference between 4-2 and 4-3, I didn't really have 4-3 on here. I could have put a limit, or I could have said this comes from a Riemann sum, set it up. But like if you combine 4-2 and 4-1, it's exactly what we're doing in 4-3 for those problems, for the limit definition.
So would you have an individual problem for 4-2 and 4-3, or would you just kind of?
Yeah, because there's other topics in both. So like we had the limit definition, but what else was in there? Find the exact area. Before we had like find the antiderivative or anything like that. So there are some other smaller topics. But as far as how we define the definite integral with the limit as n goes to infinity of a Riemann sum, that's combining, that's why I think these as my two problems. They're the biggest idea. That then shows up in another section. But then there are those smaller examples. So I will pick and choose based on, I know, since one of the problems is use the limit as n goes to infinity to calculate this definite integral. You will have less problems that do stuff like this. Now, finding area like this where n is 3, n is 4, something like that, that is definitely going to be on there, right? Like we spent some of you spend a lot of time in the homework drawing 3 or 4 rectangles and adding them together. Some of you spend a lot less time drawing rectangles. Definitely look back at how to do that. Or, like to me, I don't consider those equivalent. Setting n equal to 4 and setting n going to infinity are very different scenarios. All right. I wanted to go over second quiz. So we had the 2 quizzes. It's most of the content, thankfully. Like 4-3 wasn't on here and 4-6 isn't on here technically, but 4-3, a lot of that is what is the definite integral, and then what were the examples? Ones where you could just find the area because it's a triangle or a circle or a square, and then ones where you could do the Riemann sum and take the limit. All right. How do we determine if this type of statement is true or false? What does it mean to say this indefinite integral is equal to this? Yeah. Yeah, we take the derivative. It means if you put an f prime of x here, this must be f of x plus c, right? Should I try to integrate this?
No. Why would you do that?
That's a good general question that I wondered myself when I was grading. Don't ever just try to, if we tell you what we think the antiderivative is, just see if that checks or not. And if you like make a mistake when you're checking it, because for this one, say you got the product rule, that's going to be worth more points because you made some mistake there, but you knew what you were doing. Than if you tried to integrate. Because if you tried to integrate, you probably broke a lot of rules. The only way to integrate this is to use integration by parts. That is definitely a calculus B concept on how to do that. This isn't one where you can just come up with the answer. So if we're saying the derivative of this must be this, just take the derivative of this. See if it works out. All right. The big one is when you take the derivative of x times e dx, you have to do the product rule, right? Once you do the product rule, these cancel off, and I get exactly my integral. So that means it must be a true statement. The indefinite integral of this is exactly this family of functions with the plus c. All right. How would we solve this integral? So that's the one for finding antiderivatives. So here we have to find the antiderivative, right? What's our, how do we do that? What should be our go-to?
Take one of the x's out first of all.
Yeah. So in general, if you want to find an antiderivative, what's the first thing you look for? Power rule. Can I do a power rule? Like power rule is the one I really know. Kind of like when you did power rule for derivatives. If I gave you a polynomial, you could run through the power rule. That was the problem you would hope for. Look for a power rule. Is there a way to make it a power rule without like making rules or moving things or doing something you're not allowed to do? For this one, can you do a power rule? Anytime you have a fraction where it's just the x on the bottom, you can break it. They have a common base, right? Which means I could write it as two fractions. When you write it as two fractions, you get exactly this. So I had 1 power on top, 5 on the bottom, so I end up with 4 on the bottom. Why would I want to do that? What is the first one now? Looks like a power rule, right? What about the second term? What if I tried to do the power rule there?
No, you're gonna get rid of the x.
You add 1, negative 1 plus 1, get 0. Can you divide by 0? We still try not to do that. So what would that tell you? That's one of those where you need some other rule. So then, if I need something else, what do I know that has the derivative 1 over x?
ln of x.
Natural log. So this is one you just have to memorize. But the nice thing is, if you try to do the power rule without paying attention, you divide by 0. The second you divide by 0, you know, hey, I made a mistake here. I should relook at this. Right. You do need the absolute value, technically. Before, we almost never had that. When we were taking derivatives, we just wrote it without absolute value. So to be more general, you put absolute value. And then this one, I can just do the power rule, right? Negative 4 plus 1, then divide by negative 4 plus 1. Which is the one where people lose half points because when they add 1 to negative 4, they get negative 5 somehow. It's easy to do that in a hurry. So I get negative 3 here. Always go for the power rule. If you can see a power rule, try to make that one work. If you can just do a little bit of arithmetic and make it nice power rules or break it up into more simple problems, that's our go-to. When that doesn't work, that's when we start looking at more advanced techniques. And what are the more advanced techniques? They're pretty much all guess and check. We haven't covered rigorously how to do a bunch of them yet. The next thing would be, actually the easy ones that kind of pop out, did this come from a quotient rule? Does it look like a quotient that would come from that? Because then you can kind of guess, or when you do the quotient rule, it tells you what the bottom is. So at least you know what to guess. But then you can quickly do guess check there and say it works or it doesn't work. A lot of them are special derivatives. So, like the derivative of 1 over square root of 1 minus x squared. Or sorry, if I had 1 over 1 minus square root of 1 minus x squared, I know that looks like the derivative of inverse sine. So I definitely go back in Canvas, it had a page where it was just all the derivatives. Go back and look at that. Make sure you know what they are. A lot of them are just special ones that come up, and we need to know what those are to see them. If I want to integrate cosine, I know cosine is the derivative of sine, so I don't actually have any work there, right? It's just one of those you have to memorize the derivative to then be able to go backwards. And then when none of that works, then I start thinking I probably have to undo a chain rule. What can I make it look like to be easy working the chain rule? Which shows up on the last problem on this one. So I'll talk about that in a minute. Alright. Number 3, how do you find the signed area of a function? Antiderivative, plug in the bounds. Is there a quicker way to write that? That is the definition of a definite integral. So if I ask for signed area, it's really find the definite integral. So set up my definite integral here, then the question is how do you find the definite integral? You find an antiderivative. So what would be the antiderivative here? I can just do the power rule. Add 1 to the power, divide. What's the antiderivative of negative 4? You have slope negative 4 always. That came from the line minus 4x. And then technically plus c. Do we ever need to write plus c when we do this? No, because we're plugging in the bounds anyway. So for definite integrals, you don't have to worry about plus c stuff. Alright, so I found an antiderivative. Now I plug in my numbers and subtract. So plug in the 2, plug in the 0, subtract, I get 8. How would this change if I said find the total area or absolute area?
You'd have to do the absolute value.
Put the absolute value here. And then what would I have to do then? Now I have to get rid of the absolute value, right? How do you get rid of absolute value in this?
Find where it's positive and negative.
Find when it's positive and negative. Break it up into multiple integrals, one where it's, or break up the bounds, find the positive pieces, the negative pieces. Anytime it's negative, subtract to make it positive. So break it up into its pieces and then add them all together. So signed area and absolute area, the difference is whether you put an absolute value. But then the absolute value makes it a little harder to get rid of the absolute value, right? So that's what we did in 4.6. How do you get rid of the absolute value to find this value? Alright, last problem. We want to evaluate this definite integral. So, because of this divide by 2 on the inside, I can't just say this came from a chart of values, right? Or a chart of derivatives. But if I'm looking at it, what do I think the antiderivative of cosine is?
Sine.
Sine? So what are my 2 guesses? If I didn't even want to do any work, what would I guess here? I would guess the antiderivative is this times 1/2 or times 2. Like, I don't know what that divide by 2 does, but in the end, I'm either going to multiply or divide by 2. And then I could take the derivative of each of these and see which one works. So I could just do guess and check. I kind of know it has to be sine of x over 2. And then I'm either going to multiply or divide by something that fixes it. By a constant. Or it can be a little more systematic. I have cosine of x over 2. I'm treating this as my inside part, right? If this is inside, what would happen when you do the chain? It's also going to be on the inside when I take the antiderivative, right? So if that's on the inside, when you do the chain rule, you multiply by the derivative of the inside. So I need to multiply by 1/2. So I want to put that 1/2 right here, so that this came from a chain rule. Another way to see it is with the 1/2. I really want cosine of x over 2 times the derivative of the inside. That one I know how to integrate. But if I put a 1/2 here to get this term, can I just randomly multiply by 1/2? Or does that change the value? That change it, right? I want a 1/2 there to rewrite the problem. That means I also need to multiply by 2 to get rid of it. So I really am doing 2 times 1/2, 2 divided by 2, to make sure I'm not changing. I can multiply by the number 1. But I'm going to write it in a way that helps me. So then what happens with the 2? That one I can just move outside. You can always move numbers outside the integral sign. X's have to stay on the inside. Number 2 I can move outside. So that lets me rewrite it like this. Why would that be useful? Now I can basically say what is the antiderivative, right? The derivative was cosine of something times its derivative, times the derivative of the inside. So what's the antiderivative? Antiderivative of cosine is sine. This must be the inside part. If I wanted, I could check this real fast too, right? What's the derivative of sine? Cosine? The x over 2 stays. And then multiplied by through the inside, so it would be this. This was a chain, this going from here to here is just doing a chain rule. So I rewrote the integrand to have this chain rule built into it. This is by far as hard as this gets in my mind. Making sure the inside part looks correct in the integrand. But then what did we say you could do instead? Guess and check. I'm either going to divide or multiply by 2. Here, you find out you need to multiply by 2. So I explicitly showed this must be multiplied by 2. The other option is guess you multiply, guess you divide, take the derivative of each, see which one works. So if I only have 2 kind of logical answers that would possibly make sense, take the derivative, see which one checks. Alright, then what's left? So I found my antiderivative. Now I just need to plug in the bounds and subtract. So I plug in pi over 2, plug in negative pi over 2. Hopefully I know the unit circle. Maybe, maybe not. If you have a calculator and you give me, so it always says find the exact answer. The exact answer should have things like 2 plus root 2. If you give me the decimal, I'm going to count off a small amount. But I'm also not going to give you no credit. So if you really have no idea and all you can do is plug in the calculator, you get most of the credit. The other one is you could probably guess what it is. Say I plug in sine of pi over 4 and I get negative root 2 over 2. What's that decimal? Like negative 0.7 something? It's always the same decimals that show up when you do root 3 over 2, root 2 over 2, pi. If you start memorizing those decimals, you know what the exact form was.
At that point, it might be less memorizing.
Well, now let me, you know answers are root 2 over 2, root 3 over 2, pi over 2, things like that. So, what can I do? Type in my calculator what is root 2 divided by 2 and see if the decimals match. So yes, in some sense you can memorize it, but it's also we only have like 5 numbers it could be. Just plug those 5 numbers in your calculator, see which one agrees. So.
I mean, I don't even memorize the unit circle, I just remember those numbers and then I memorize, and then I know how the different quadrants change the signs.
Yeah. Yep. It's good enough. Especially because without calculator. Yes?
Well, cause I have like a special trick in my mind. So like cut, and of course you have to remember how the signs change depending on which quadrant. But basically, like pi over 6, for example, cause it has a denominator of 6, so it has the 1/2, and then the 3, or square root of 3 over 2, like that's coordinate. And then the ones with a denominator of 4 always have the double root 2 over 2 as the coordinate. And then the ones with a denominator of 3, they're always going to have root 3 over 2 and then it's going to be 1/2 and then root 3 over 2, like as that coordinate.
Yep.
And then you just have to remember which quadrant, and then from there you can apply like the actual like sign, like from based on the quadrant.
Yep. I always go. I know it's one of these 5 numbers. It's always one of those 5 numbers with a plus or minus sign. And then I know what these decimals are. So you actually don't need to know anything, you just check that way. Or actually, that's not how I do it in my head. How I do it in my head, pi over 6 is closer to this axis. So the x coordinate should be bigger than the y coordinate. Which number is bigger? Root 3 over 2 is bigger than 1/2. If I'm closer to this axis, my x coordinate should be the smaller one, my y coordinate should be the bigger one. When I meet in the middle at pi over 4, they have to be the same thing, so root 2 over 2. Like, if you know those 5 numbers, you know what all options are. And 0 and 1, I can definitely recognize those when I plug in a calculator. It's only those 3 were round. Actually, 1/2 is going to recognize that one too. Alright, so that was that quiz. Any questions, anything about what to expect? I like this true-false problem because I've been told I have to include true-false. So this one we could set up. It's a standard problem that I can just say you write the word true or false. So. Alright, any questions? Anything you want to talk about?
We're gonna have probably see it bounded between f and g, Helio.
Yeah, it'll either be here's 2 functions, find the area between, or it'll be absolute area. One or the other. So I'm not going to include lots of. It's only going to have 1 or 2 questions from a section typically.
Plot twist: you make one of the f of x is normal, but then g of x is like equal to 0.
Yeah, I could do that. Actually, I always think that all these are you're setting g of x to be 0. When you say with the x-axis, that means you set g of x to be 0.
Usually, for the most part, it looks like there's some g of x or something here, then we usually just subtract it.
Yep. Well, you have to put absolute value.
Yeah.
But yeah, when it's
just to get a positive.
technically you only have to do this, and then you can find what is f minus g, and just treat that as a new function. Find the absolute area of that function. Yep.
Okay, thanks.
Yeah, that's where those are in some sense the same problem. They don't quite look that way though.
Yeah, I usually get
Yeah. That's.
I personally like whenever you're doing to find the area between 2 functions, right?
Yeah.
And you have one they like switch who's on top. You need to know to set up your intervals correctly. You need to know where they intersect, right?
Yes.
What is the best way to setting them equal to each other and
Yep.
and setting them and find a way to make one side equal 0?
Yeah, you either set f equal to g, or you could say always work with f minus g. So treat this as its own function, call it h. When they intersect is the same as saying h of x is equal to 0. So then you're just finding when is h positive or negative. So instead of doing f and g, you can treat it as when is h positive, negative, and treat it just like what we did in chapter 3. Because then it's when is h 0, when is h undefined. Undefined doesn't come up in this chapter, but that makes it look like something older. There would be like a page of find antiderivatives. You'll randomly have to find some definite integrals here and there. You will definitely have one where it's here's some graph, use left, right, midpoint, trapezoidal, one of these rules to upper or lower, one of these rules to find the area or approximate the area. But you'll have the graph. So make sure you use that to your advantage. If I didn't give you a graph, it would be a function where you could sketch the graph quickly enough to then at least check yourself. But I believe the only one I put on the test, I give you the graph. There are some where you can find the exact area without doing antiderivatives. It's like when you have a line or something, if you can basically make it look like a triangle or trapezoid or circle, we know these area formulas. You don't even need to do the or you don't need to find antiderivatives or anything. Anything else? What else did we even cover? We drew a lot of rectangles. In the homework, some people drew a lot more than others. Some people did like 2 problems where they drew rectangles all over the page and were like, oh wow, this is awful, and skip the next 4. It happens. It is that level of tedious. Don't confuse tedious with hard though. And on the test, if you do have one with like a bunch of square roots and all that in the sum, read directions. It may say just leave it. You don't have to find the decimal. I'm seeing if you know what numbers to plug in. All right, so don't waste your time. Always read the directions. Don't waste your time making the problem much harder than it is. All right. Anything else? Any questions?
Is there any way that, like, you wouldn't ask a question where we have to use the definition of the Riemann sum as n goes to infinity, but also you'll tell us that we have to use something like, we can't use reference.
Nope, it will say, here's f of x, find it'll either say find this using the definition, or as a limit of Riemann sums. I just say as a limit of Riemann sums, and I don't tell you which one to use, so I would use the right endpoint method. But the question will be either evaluate this, or it'll say find the signed area of f of x between a and b with the x-axis. The same wording we had on that quiz problem. It'll be 1 or 2 of those, and it'll just say using limits and Riemann sums. So that's how you know to use the definition. And then how do you set that up? It'd be the limit as n goes to infinity of the sum f of x k star delta x. But then if you do the right hand rule, you can just make that xk, which is what I would do. And then what the problem really becomes, do you know how to find xk? Do you know how to find delta x? Once you do all that, then you can use those formulas at the bottom of the page when you simplify it. So I'm checking, when I go to grade something like that, I'm checking, do you know the process? Did you get the setup right? That is actually in some ways worth 1/3 and 1/2 the credit of, did you just get the setup correct? Because otherwise the rest you can't do anyway. So I usually weight it a little more heavily towards the beginning part. And then did you know how to take a limit and plug those formulas in for the last part? Right. There is one of those, so definitely study that. It's either 10 or 12 points. 15-minute tests are hard. Problems have to be worth more than you want. Alright, any other questions? You kind of know what to expect? Alright, your test is tomorrow. When it's over, you can run home and have Thanksgiving. Unless you have another class.